Okay, welcome back to track 1, part 2, Kodiak, not McKinley. And we're in the second half now, and I am so stoked to be in this track because I'm learning stuff, and I'm learning stuff that's cool. Next up, we have Rob Turner from Qualcomm, who's going to teach us about hardware mitigations and things like that. So round of applause.
Oh, good day. Am I mic'd up and audible? Yeah. Cool. All right, well, good day. I'm Rob. I work for Qualcomm in their product security team. It's a pleasure and an honor to be here and have the opportunity to speak with you. I think in about 50 minutes, I'll start really enjoying the conference. My title is a little vague, and I haven't managed to find abstracts anywhere. So to give you some idea of what I'll be talking about a hardware extension in ARM v8.3 called pointer authentication. So it is necessarily specific to ARM, but I think the underlying ideas are interesting and of general interest. I'd think of it more as a software security talk than a hardware talk, because it's a hardware extension to solve a software security problem. I was shocked to learn recently that some people find the intricate details of hardware extensions to be a somewhat dry subject, and I don't understand these people, but I hope that if you're one of them, my enthusiasm for the subject will be contagious. This is an old deck. So maybe I can... This looks better. All right, so here's the agenda. Based upon what I've seen come out of MSRC over the last few years, Microsoft as an organization understands the value of mitigations. So without any preamble, I'm going to jump straight into the design of pointer authentication. I've pitched the talk for an audience that's already familiar with stack smashing protection, data execution prevention, address space layout randomization, and at least at a very high level control flow integrity. So you'll get the most out of it if you're kind of already familiar with some of those ideas. After talking about the design, I'll talk about the cryptography that's involved. I'll spend some time talking about the security that the extension offers, and then I'll wrap up with some of the ways we see it being applied. Good news is that I updated the presentation and didn't go back to update the agenda. So the last two sections, there are fewer slides there than it says. So we're going to start with the question, what's in an ARM v8 pointer? And it would be reasonable to assume that the only thing in a pointer is the virtual address of the object that's being pointed to. But that's not quite the case. ARM v8 through ARM v8.1 supports 48-bit address spaces. And in ARM v8.2, they added an extension that lets you go up to 52 bits. But this still leaves 12 bits that aren't part of the virtual address. And if you spend much time with hardware folk, you learn that kind of unused bits makes them uncomfortable. They try to cram as much stuff in as little as they can. So it turns out that the upper byte also has a use. There's a feature of the processor called address tagging. And if you enable this feature, it lets you store any kind of value in the upper 8 bits of a pointer that's totally ignored during address translation. And an example of why you might want this is you could store, say, type information of what the object being pointed to is, and this may let you have more efficient checks in a dynamic language. This bit 55, this is a very important bit. They use, well, ARM, I guess, like Intel, supports in some execution levels. They describe them as translation regimes. But really it just means you can have two address spaces, a lower address space and an upper address space, which is often used for user space and kernel space. This bit is how they decide which address space we're in, and it's also used to select different sets of configuration registers for the different address spaces. If this bit is 0, then all the unused bits must also be 0 for this to be a valid pointer, and similarly if it's 1, they must all be 1. If this isn't the case, then when you try to translate this address, you get an address translation fault, and that will become interesting later on. So Here highlighted are all the bits in a pointer that have some kind of architectural significance, which leaves 3 bits that don't. And this was, I guess, the seed of our idea. This title is, I go back and forth on whether it's a pun. The main idea is let's use the unused bits in the pointer as an authentication tag or an authentication code. And we can verify this code before we dereference the pointer. In this way, we can guarantee its integrity. And for this, we need 2 operations. The first will compute the authentication code and tag a pointer with it. And the second one will recompute the authentication code and compare it with the value stored in the pointer. So hold on, the attentive audience says. I've just told you that there are 3 unused bits in the pointer, and I want to use it for an authentication code, which is silly because this means 1 in 8 tries I can guess the authentication code. So the situation's slightly better than that. This is the worst case. But we take advantage of any available bits that aren't being used for anything else. So if the address tagging feature is disabled, we go up to 11 bits. And it's also possible to configure the processor to use smaller address spaces. So you can end up getting between 11 and 31 bits depending upon how large you want your virtual address spaces to be. As an example, in the default configuration of Linux, they do enable address tagging, and they have 39-bit address spaces. So in Linux, with the default configuration, you would end up with 16-bit tags. So hopefully, to some extent, that assuages the fears of just guessing the value of a tag. For the scope, we considered only 64-bit ARM because there just aren't enough bits to play with in the 32-bit variant. We needed something that was minimally invasive. So this means we were shooting for something that was as transparent as possible to developers and build engineers, but not, unfortunately, for compiler developers. They have to deal with the full complexity. We wanted something that didn't add any extra memory to the system, so no tag memory or tables. And we didn't want to make any changes to either the application binary interface or to how address translation worked. We also need something that's compatible and interoperable, or no one uses what you build. By this, I mean it had to be something where new binaries and legacy binaries both run on new processes. You should be able to have either a new or legacy executable interoperate with new or legacy libraries, and they should all play nicely together. And it should also be useful for both application and system-level code. There are some groups of instructions that are added as part of the extension. The first group is the pointer authentication code set of instructions. These perform the first operation, which is to compute an authentication code and tag a pointer. And the second grouping of instructions, the auth instructions, they perform the second operation. They verify a pointer by recomputing the tag and comparing it with the tag inside the pointer. So some details on how this works. When we compute the authentication code, we are only concerned with the virtual address bits in the pointer. We don't care about, say, the address tagging, if that feature is enabled. So if this is our example, we have 48-bit addresses. Address tagging is enabled. We end up with 7 bits for our authentication code. This isn't ideal for security, but it is ideal for slide creation. These 48 bits are what we'll use to calculate the authentication code. And if we're tagging a valid pointer, these 7 bits, once we've passed it through the pack instruction, will have either zeros or 1 there, whatever the authentication code happens to be, and I represented that with question marks. If the authentication succeeds, we take whatever value is in bit 55, and we restore all of the authentication code bits to this value, so like that. And if the authentication fails, then we write a special value there, either 01 or 10, and this guarantees that when we dereference the pointer, we get an address translation fault. And sadly, this wasn't my idea, but I think it's one of the snazzier ideas, because we can reuse that mechanism in the processor to catch this particular type of flaw. And by looking at the pointer, once we've caught the fault, we can determine what the problem was afterwards. If you have an invalid pointer, as before, we calculate the authentication code But if any of those unused bits are not all 0 or all 1, then we just flip the second most significant part of the authentication code. So when you go to verify this pointer, you'll have an address translation fault at that point in time. Or rather, once you try to verify it, when you dereference it after that, you'll get an address translation fault. So that's how we deal with those different cases. And it's to stop someone from taking an invalid pointer, authenticating it, verifying it, and then having a valid pointer after that, even though they started with an invalid pointer. Going back to the instructions, there are two more groups. There's also a generic authentication code instruction. What this does is it computes the authentication code, but rather than tagging a pointer with it, it just writes it into a register. More precisely, it writes it into the upper 4 bytes of a register, and it zeroes the lower 4 bytes of a register. I thought this was really weird, so I asked them, why did you do this? Because after all, the output of our cipher is 64 bits. And it turns out the reasoning behind this is export controls. If you filled the entire pointer with the value, it might be considered general purpose cryptography, and then it would be subject to export controls. So I found this interesting because it's not something I generally think of when I'm thinking of design criteria. There's also the X-Pac Instructions. Their purpose is to strip an authentication code from a pointer without performing the verification, and the intent here is to support debugging. You might have a debugger which is attached to a process, and it won't have access to the keys that the process that's attached to is used to authenticate its pointers, so it can't verify the pointers. But if you want to, say, walk the stack, you need to strip the tags, and then you can walk the stack using existing code. A good question to ask is, why authentication, why not encryption? And the train of thought that might lead you to encryption being a better solution is the resistance to guessing. With encryption, if I'm going to guess, a valid encrypted pointer, I have a 1 in 2 to the 64 chance of doing that. Whereas with authentication, I have a 1 in 2 to the size of the authentication code. So on the surface, it seems like encryption would be the better choice. But there are, in my opinion, some really good reasons to prefer authentication. One of them is error detection. With encryption, you're relying on the fact that when you decrypt the value, if it has been corrupted, it should decrypt to garbage, and you want it to crash as soon as possible. But it may not crash as soon as possible. It could do all sorts of things before it does, and I think that would be a real pain to debug, and I wouldn't wish that on anyone. With authentication, because we can write that special bit value in there, we can determine that it was an authentication fault that led to the fault. Debugging is another reason to prefer it. Because the actual virtual address is alongside the authentication code, it's still there to be seen by a debugger, which makes things much easier. If you have, say, a core dump where the keys that you use to authenticate all of your pointers are, lost, you can still do useful things because you still have the virtual addresses. A similar argument is for branch prediction and speculative execution. Because the virtual address is in there, readily available inside the pointer, the processor can continue to fetch instructions that are going to be executed. It can fetch data that's being referenced. And this lets you keep the pipeline full, which is really important when it comes to hiding the latency of these instructions. A last argument to prefer authentication over encryption is just one of semantics. What we really want is we want to guarantee the integrity of pointers. We don't care so much about their confidentiality. So authentication gives you integrity, encryption gives you confidentiality, so prefer authentication for that reason. The last thing I'd like to say about the design is to mention this notion of context. A context is an additional public input that's used in our authentication algorithm, and it's specified either explicitly as a register or an immediate in the instruction, or implicitly by the specific type of instruction variant. And its purpose is to mitigate a pointer substitution attack. And I'm going to leave that for now, because in the security analysis section, I'll address that in more depth. What I think is cool about contexts is that they let you emulate the granularity of different CFI or control flow integrity schemes. So Microsoft's control flow guard, as I understand it, and I really hope I understand it because this would be the most embarrassing place to prove I don't understand it. But as I understand it, it restricts you for any indirect branch. It allows you to jump to functions that have had their address taken. So legitimate destinations for indirect branches, but maybe not the legitimate destination for that particular indirect branch. And you can get this same behavior with pointer authentication by using a fixed context across every authentication verification. If you want something with a more fine-grained approach, then you can use, say you could use the arity of a function. So for your context, you could use the arity of the call site, and then this would prevent you from using a function that takes 2 parameters from a call site that only takes 1, as an example. But you can emulate all of these different schemes through the use of contexts. All right, so for the crypto, we needed something fast and lightweight because the efficiency hinges on how quickly you can perform the cryptography. It also has to be strong when you discard most of the output of the cipher and you end up with very short authentication codes. And for our uses, we wanted 2 64-bit inputs, so the pointer and the context. We have 128-bit keys, and we produce a 64-bit output. We designed an algorithm called Karma, and here I'm being very liberal with the use of we. I had nothing to do with this. But we designed something called Karma. At Qualcomm, it's the height of cleverness to name something with either a C or a K and to replace the C or K with a Q. That's looked upon very favorably. Karma is a family of lightweight, tweakable ciphers. I had no idea what a tweakable cipher was. So it's a type of block cipher, but it takes 1 extra parameter, which is the tweak. And it's considered secure if, even if an attacker knows the tweak, they still can't predict the output of the cipher. So in our case, the tweak is the context. I guess they were designed originally to solve the problem of memory encryption, where if you had a block of memory that you were decrypting, you want it to be different from the other blocks of memory that may have very similar content. So they added the tweak, which was the physical address of that chunk of memory. So it comes from that line of research. For key management, we have 5 128-bit keys. There are 2 keys for pointers to instructions, 2 keys for pointers to data, and 1 key for the generic MAC instruction. Keys are not banked per exception level. So in other words, it's the responsibility of software to switch keys when switching contexts. And there are system register controls for the behavior of these keys and these instructions. For backwards compatibility, you can disable keys. You can also configure it to trap into higher exception levels when either a key is used or when an instruction is used. And the idea here was to allow things like, say, the lazy loading of keys when you're switching contexts. All right, on to the security analysis. Our security boundary is the process itself. Our threat model is we assume an attacker who has arbitrary read-write. In other words, they can, at arbitrary times, read arbitrary memory locations and write arbitrary values to arbitrary memory locations. It's a powerful attacker model, but it's also, sadly, very practical and reasonable. Our assumption is that you have data execution prevention implemented correctly. If you don't have this, then it's trivial to bypass pointer authentication because you simply overwrite the checks or you forge your own pointers by writing instructions that can generate new authenticated pointers. There are a number of attacks to consider. The first one is guessing and forging tagged pointer values. I touched on this earlier. We have between 3 and 31 bits for our authentication codes. And obviously, your ability to guess it will be dependent upon how wide the code is. If you need to guess multiple pointers for your attack, then the chance of guessing all of them will increase exponentially. And for forging pointers, because we have a cryptographically strong algorithm, it's not possible to forge pointers no matter how many how many authenticated pointers you can see. It doesn't make it any easier to forge, another one. If an attacker has arbitrary memory read, say through a read buffer overflow or an uninitialized memory vulnerability, then they can read arbitrary memory locations. Stack smashing protection and address space layout randomization are vulnerable to information disclosure, but pointer authentication is designed to be robust here. Again, because we have a cryptographically strong algorithm, no matter how many authenticated pointers you collect, it doesn't help you, create new ones. And the keys aren't stored in process memory. The keys are stored in registers, and they're not available to the lowest exception level 0. For arbitrary memory write, this would be an attacker who has exploited, say, a stack or heap buffer overflow or a use after free vulnerability, and they can write to arbitrary memory locations. With pointer authentication, we can protect sensitive pointers by authenticating them. So save return addresses or function pointers, we can prevent an attacker from, or we can't prevent them from overwriting them, but we can at least catch it when they try to dereference the pointer. Similarly, we can protect pointers to sensitive data structures. However, as attackers have proven time and time again, they will just move to the kind of next lowest hanging fruit. So they will possibly resort to, say, data-only attacks as a next step, where they, say, overwrite an is-authenticated Boolean to bypass a password check. Or if you have a kernel exploit, you might overwrite the effective user ID of your process to elevate to root. And that, that is something that is not addressed by pointer authentication, hence the title, Raising the Bar. It doesn't entirely solve the problem, but the hope is that it will make exploitation either totally impossible in some scenarios or prohibitively expensive in others. The most interesting class of attacks we think will be pointer substitution attacks. Any pointers that are signed by the same key and with the same context are interchangeable. So a pointer substitution attack would involve the attacker leaking an authenticated pointer and then overwriting a different authenticated pointer with the leaked pointer. An example of where this may be a problem, let's say you have a program with complicated logging needs, and it can choose to write its logging output to either the console, a file, or a socket. The programmer might have decided to abstract this with a function pointer that can point to any of these three things. And if you also assume that at some point this program takes the address of the system C standard library function, then an attacker who can leak the authenticated pointer that points to system, and they can overwrite the logging function pointer, and I guess also control the input to the logging function, they could still get arbitrary code execution even with authenticated pointers. There are a few ways we've tried to mitigate this. The first is by having 5 different keys, 2 for instructions, 2 for data, and 1 for generic use. It's not specified how to use the 2 different keys, each for instructions and data. We're hoping that there will be, I guess, some creative ideas in that space for good ways to, use one key for one set of operations and another key for the other set. The other way we attempt to mitigate this is with contexts. And if you're designing a mitigation that makes use of pointer authentication instructions, you should make as much use of context as possible in order to mitigate this threat. As always, there are key management concerns. You want your keys to be strong and not predictable. So generate your keys with a good pseudorandom number generator and have it available as early in the boot flow as possible. If you reuse your keys in different processes, you have a problem, so don't do it. Other problems are interpreters. If you have a function like system, for instance, and you can supply your own input to it, it's game over. And just-in-time compilation can also present a problem because in not all implementations, but in many implementations, they violate our assumption of data execution prevention. They'll often have a page of memory which is both readable and executable and writable at the same time. And if you can do away with our assumption, then you can break the scheme. So that was a monster slide. There's only about 15 words on the slide, but I must have said a few hundred, so well done. All right, in terms of applications, we expect this to be used in secure execution environments like TrustZone. In these environments, it's reasonable to have a smaller address space where you can take full advantage of the larger authentication codes. And this does mean that we are essentially trading 1 bit of ASLR for 1 bit of authentication code, but we think this is a worthwhile trade-off because ASLR is vulnerable to information disclosure, but pointer authentication isn't. So it seems a worthwhile trade-off. I think the most reasonable way to expose this to developers is with compiler instrumentation. So flags like -f stack protector, something like that. And this would be a good way to expose stack protection that takes advantage of pointer authentication or control flow integrity. A less useful way of exposing it is with compiler built-in to let you get at the instructions directly. And this might be necessary if, say, a library designer decides that this pointer to this data structure or this free list should be protected. They can get at the nuts and bolts through built-ins. But from my own experience, this is a little unwieldy to use. I think a more intuitive interface is with attributes in the compiler. So you can attach, say, like an authenticated attribute to either a type or a specific value, and then the compiler would know to generate the appropriate instructions when you either assign a value to that pointer or when you dereference that pointer. So as an example of how this could be used to implement a generic countermeasure, with pointer authentication, we're going to tag the save return address, and for the context, we can use the stack pointer. This means that it's not possible to substitute one authenticated return address with another unless they happen to fall at the same stack slot. So without SSP, your prologue and epilogue look like this. With software stack smashing protection, there's a few things to notice. The first is that the frame size increases because we now have the stack canary inside the stack frame. And there's also a host of extra instructions because we have to load the canary from thread local storage, save it onto the stack, and in the epilogue we have to again load it, do the comparison with the golden copy, and then, if necessary, handle the error or continue execution. With pointer authentication, it's still worse than no instrumentation, but it's better than the software version. We add one instruction. This is a variant of the pointer authentication code family of instructions. It uses the key A and implicitly uses the stack pointer as its context. And we replace the return instruction with RET-AA, which also uses the A key for instructions to validate the pointer. It's an example of a combined instruction. The combined instructions do an authentication and then either a branch or a load in a single instruction. And there were two ideas here. One is to reduce code size, and the other is that it prevents you from creating gadgets where you have an authentication and then sometime later a branch. Anything between these two operations is a potential gadget. And I'm not too worried about that, because in order to jump to this gadget, you would first have to, break the scheme. But this would make it more difficult for someone to string together multiple gadgets if they can do it in the first place. Also worth mentioning that PAC-IASP and some of the other instructions, their encodings come from the NOP space in previous versions of ARM. So if you were to take this code on the right and run it on an older processor, it would still work. It just wouldn't give you any security benefit. That's not true for all of the instructions that have been added in the extension, but it's true for a subset, the ones we thought would be most useful. Other places that could potentially benefit from this, you could authenticate addresses in the import address table. And in the C standard library, there are numerous things that might benefit from this. So one example is jump off structures that are used by the set jump and long jump functions. Another example would be the add-exit callback. You could protect that pointer in memory. I do hope, by the way, that you appreciate my attempts to cater to Windows. I had to look up the PE file format to find like the relevant names of things. There's also APIs. So you guys have encode pointer and encode system pointer and the corresponding decode functions that right now use exclusive OR with a key that I think is stored in the operating system. You could augment that with pointer authentication. And similarly, glibc has a pointer mangle macro that it uses for pointers that are stored in memory. You could do pointer authentication there instead. And best of all, tagging every possible pointer would be where I'd like to see this go. All right, so to conclude, and I'll try to talk slightly slower because I have a lot of time to burn through. So pointer authentication, it's a new primitive that you can use to build software security mitigations. It's useful by itself, but you could also use it to build stack smashing protection or control flow integrity, kind of other countermeasures. As usual, the best results will come from understanding the application that you're trying to protect and knowing which pointers should not be changed. And I guess one of my personal takeaways from this is it's always beneficial to spread an idea as widely as possible before you do something silly like standardize it so it can't be changed. Because I come from a mobile background, and there were things that I did not think about, like nested virtualization and VM migration, that luckily other people did think about. So that, for me, is one of the kind of more important lessons from having worked on this. And I leave you with this, because I think it's funny. Huh. All right, so thank you for your attention, and I'd be happy to take any questions.
And we thank you for including a meme or Twitter reference to wake us up. So, okay, questions. We have lots of time.
Hi. You talked briefly about switching some ASLR bits over to authentication bits. Can you talk about, do they fit together? Is ASLR sort of less necessary if you have signing? Is it unnecessary if you have signing?
It's definitely not unnecessary because there still are, say, data-only attacks. If I have to choose between just one of them, I'm going to pick pointer authentication because it's my baby. But I also think that there are some advantages to that, namely that it's resistant to information disclosure. It would be ideal if you didn't have to make that trade-off at all.
Thanks.
I'm just trying to understand it, like, a little bit in details. You said that worst case scenario is 3-bit free, right? Mm-hmm. How hard it would be to predict that some process runs under these circumstances? Because attacker typically goes after easier target, right? Mm-hmm. And in this case, despite the fact that you probably need to protect several pointers, 3 bits for several pointers, it's still constant time, right? So there's... Am I understanding it correctly?
I think so. Your chances of guessing multiple pointers, I guess, decreases exponentially. But if it's only like 2 to the 3 each time, it's not so great anyway. Typically, most processors on the system will have the same address size. I think you could have an operating system where that wasn't the case, but I'm not familiar with any that work that way. I guess I look to the default configuration for Linux where you have 16-bit, would have 16-bit authentication codes as like a promising example. But I think really to be maximally useful, you have to plan to use this ahead of time, and you have to... It's most useful where you have the flexibility to choose a small address space. So in something like Trust Zone, that seems very reasonable. In something like Windows, I'm not sure how much of the address space you take advantage of, but it may be so much of it that it would be very difficult. I mean, I don't think you can go back to smaller address spaces now you've kind of made that decision. I don't think that's a reasonable choice.
So just follow up for this, because it's ongoing project, and if you open for suggestion, because sometimes developers doesn't think about, it's good strategy to use protection of pointers, but when you compile and all, as you suggested, to have additional flags into it, maybe developer needs to know that, you're limited in address space, and maybe it's not the very secure option for you, and you want to consider something else in this case. Because, if you just go in for this and take it as best practices, and you happen to be 3 bits for your token, you're basically screwed up. But yeah, thank you very much for interesting talk.
I think it's very reasonable, though, that people, I guess, appreciate what they're getting and not getting. So I agree.
Hey, so what kind of overhead would you get by adding this? Because it seems like calculating that hash every single time would be a lot of overhead.
So I'm not sure. It's easy to calculate code size overhead. It's more challenging to measure the performance overhead. In the Karma paper, he gives you a metric in terms of the number of gates, but for me, that's quite useless. I guess it kind of remains to be seen how the different microarchitectures kind of optimize. I'm hopeful that because we don't upset either branch prediction or speculative execution, we can hide most of the latency of these instructions with pipelining, but we'll have to see.
Yeah, I was thinking also maybe additional hardware just for that or something could help.
Yeah.
Well, thank you for your talk first. Right in the talk before, we presented how to get control of the program counter by using fault injection technique, so without smashing stacks or things like that. So basically, the program counter is immediately ejected on such a success fault. I think it's useful to share for the audience that if you actually apply full CFI to the code by tagging everything, basically, we would not have a way of jumping anywhere in our attack. So this means that it would also help to mitigate what we are doing. But as long as you don't leave one unpatched, one CFI untagged space or code, because we have full control over the PC counter in the way that we want, we'd always be able to jump there and then probably at this point remove some other protection and so on. So just a note also from the previous speaker that this might be useful also for counteracting our own attack, but only if you apply full control flow integrity to your code. That's an addition to your talk as well. Thank you.
Well, thank you for your questions. I didn't have to use my audience plant. So.
Hey, there's one more question.
What?
That guy has a question. One more.
Sorry, I'm slow. I'm not a processor guy, so forgive me for stupid questions, but the scheme you're proposing applies only to certain targeted instruction sequences. Why not apply it at the processor translation level for all pointers and basically require that essentially every pointer that we use? Because a number of the attacks that I could think of, I'm not going to bother attacking. If I'm going to do a data-only attack, for instance, I'm not going to bother attacking the encrypted pointers. I'm just going to use the unencrypted pointers that give you the same benefit. You know, I guess the only way that I see that this makes sense is if you've encrypted every possible place where there's a code flow indirection through a pointer. So why not encrypt all code flow indirections through pointers?
So that's what I hope happens. But as to the question of why not do that like without explicit instructions, why not just do that implicitly? That's an interesting idea. It's not one that I considered, or as far as I know, was considered. I guess let me think about that. And if I can think of a good reason for why that isn't a better way to approach it, I'll let you know. But it's another good reason to socialize ideas as widely as possible, because sometimes people who aren't processor guys have great ideas.
So partially a response to the previous question. I don't think at a processor level you can automatically distinguish pointers with unused bits from other 64-bit values, and you don't want to be overriding random 64-bit values. But also, it does have. These operations do have a cost, right? So you want to leave it up to the developer how much they want to pay for hardening their application.
Hi, nice presentation. I'm mostly an x86 guy, so I have not programmed much in ARM. But if the pointer authenticate fails, is there any exception that is raised? Or if I'm going to use unauthenticated pointer, what kind of exception going to be raised on the ARM processors?
So if you attempt to verify a pointer and the verification doesn't succeed, then we write a special value where the authentication code used to be. And if you then use this pointer, it's guaranteed at that point to trigger an address translation fault. So you don't learn that there was a problem at the time you authenticate the pointer. You learn, or verify it rather, you learn that there was a problem when you use the pointer later on.
So you get a page fault with a special error code? Or
so I'm not sure if you get a special error code, but the fault you get, by then looking at the pointer that caused the problem, you can see that special value and determine that it was a pointer authentication problem as opposed to just an invalid pointer that you try to dereference.
So the linear address gets presented to the kernel or whatever?
Yeah.
Okay, thanks.
Hi, two questions. One is, have you talked to Ken Johnson here at Microsoft about this yet?
No, I haven't.
Fantastic. I'll come down after and give you his email address at least. He was one of the major people who coming up with CFG and some of these other mitigations, and it would probably have some good input for you. The second one was, so from what we were saying is, when you go to decode the pointer, if the authentication check fails, you get a special value, but you don't throw an exception at that point, which makes sense. So therefore, you have an oracle, and the 3-bit case is trivial if you're already executing code, which is what we're trying to prevent in the first place, right?
Sorry, can you repeat that?
The decryption, the authentication check can be used as an oracle, correct? You can run as many as you want until you try to actually dereference the pointer. And then you can check yourself for the special bit pattern.
So yes, but you're kind of assuming that you already have control over the flow of the program.
Which is what we're preventing with this feature in the first place. Got it. Okay, thank you.
And I guess just a comment on interactions with Microsoft. I meant to mention this in the security analysis part, but when this idea was given to other ARM partners, the Microsoft security team actually described like a pointer substitution attack in a browser environment, which we talk about in our white paper. And I'd like to say we address it, but really we just kind of say browser security is really hard, and we acknowledge that this is a way you can attack this idea. But they made that contribution to the design And I asked the compiler team, the Visual Studio team, if they were going to implement this, and they gave me a very kind of politic answer, but I think they wondered who I was. So, yeah.
If you talk to MSRC, you eventually talk to Ken Johnson.
Cool. Thank you.